now that we understand counting sort, we can talk about what's the oldest sort that I know of at least, something known as LSD Radix sort. This goes way back to the earliest days of automatically tabulated censuses in the United States, and probably goes back farther than that. But in terms of automated sorting, this is the oldest sorting algorithm, I think, that's out there. The first thing that was ever totally implemented completely automatically for sorting real data. So, as you know, not all keys belong to a finite alphabet, for example, a string. However, I will note that each string, it is a sequence of digits or a sequence of characters from a finite alphabet. And that idea could be generalized. So for example, let's say rather than having a single card suit or number, we have a string for each. We have horse, elf, cat, crab, monkey, rhino, or spade, spade, heart, diamond, diamond club, or 42,387, 34,163. As you can see, in all of these cases, we have, in theory, an infinitely large possible set of keys because we can have an arbitrary number of digits, but each digit itself comes from a finite alphabet. That's going to be what we're going to rely on in order to generalize counting sort. Okay. So, in particular, this version of radix sort is going to be called LSD, or least significant digit radix sort. And how it works is we're going to sort each digit independently, starting from the least significant digit and moving towards the left. So just to drive home that term, in the number 43,415, what is the least significant digit? It's 5. That's the least significant. And so we're going to use that generalization to mean the rightmost digit. Okay. So for example, here, if I sort these folks by their rightmost card suit, we'll end up with all of the spades, all of the clubs, all of the hearts, and all of the diamonds in the least significant digit position, as shown, right? So it's sorted by the least significant digit. Now, is this sorted? No. But it's getting us somewhere, okay? If we then sort by the most significant digit after sorting by the least significant digit, then we will end up in sorted order. So, for example, club spade is the smallest value out of all of my keys, and diamond spade is the largest out of the particular set that I have shown. Okay? So if you look here, you can see they're all sorted. And what happened was on that second pass, when we sorted by the most significant digit, right, it meant that these hearts were able to move ahead of all of the clubs and spades. So they ended up here. And because counting sort is stable, which I think I neglected to actually say out loud earlier, because counting sort is stable, they don't cross over. So we end up with, ultimately, all of the hearts in the most significant position being clustered together, and with respect to them, they are going to be sorted by least significant digit among that subgroup because they were already sorted that way. That's the heart of stable sorting. So the first pass is just to make sure that when the second pass happens, that everything is in the appropriate sorted order within its group. So this is the club group, the spade group, the heart group, and the diamond group. Okay? Maybe it's easier to see with numbers. So it's the exact same thing. Right? If I just do 1, 2, 3, 4, I'm just going to show it again. If I sort all of these items by their least significant digit, everything with a 1 in the right digit, 2 in the right digit, 3 in the right digit, and 4 in the right digit are all clustered together. And then when I sort by most significant digit, well, that means all, for example, of the 30s end up here, and all the 40s end up here. And because we already sorted by the least significant digit, that means that the 30s are going to be sorted with respect to all the items in that 30 group. Hopefully that makes sense. So that's all LSD sort is. You sort the rightmost digit, then the next digit, the next one, move to the left, and it's guaranteed to be correct. Okay. So what is the runtime of this sorting algorithm? This is called LSD for least significant digit sort. So what I'd like you to do is pick the appropriate letters that you'd like to represent non-constant terms. So you'll need N, but you might need something else. This is a vague question. It's a hard one. So let me know what you think the runtime of LSD sort will be. So I'll give you a hint real quick, which is that here we did 2 passes of counting sort. So think about what the runtime of 2 passes of counting sort would be, and then generalize. Okay, so the answer I came up with is theta wn plus wr. Why? Well, remember that counting sort is n plus r, and w is the variable number letter I picked to match our optional textbook. Maybe you would pick D, I don't know, or L, whatever would be fine by me. But here w is the width of each item in terms of its number of digits. So here w is 2, so the overall runtime would be 2 times n plus r, and if I just distribute that out, I get wn plus wr. So I think it looks slightly nicer. You could also write it as w times n plus r, theta, all of that, same thing, but I like it better this way, and it also matches our optional textbook. So the runtime of LSD sort is just w times n plus r. All right, now there's one little issue, which is, let's say that the keys are not the same length. Okay, let's say we have, for example, 43, 9, 817, 412, and so forth, and we sort by the least significant digit. So after doing so, we have 51, 71, 412, 43, 33, 817, 9. Okay, now at this point, it's like, what do we possibly do? So we've sorted by the least significant digit, but here, there's no middle digit. So what should we do? So maybe you already can imagine this, but we can basically treat an empty space as a character which is less than all other characters. So you could think of it as 0. These dots are the same thing as 0, at least with the number case. But in general, it would be, you just make up an imaginary character that is small, that is less than all others. And the analogy is 0. And so in this case, when we start, we can imagine just padding each of the characters, each of the keys with however many dots it needs to get to be the max length. And so, for example, 9 becomes ... 9. And that means that when we want to sort by our middle digit, well, we're going to use a dot as the value that's this key's middle digit. So since this is less than everything else, it's going to end up at the top. And now again, we have a bunch of numbers that all have dots. You can think of them as leading zeros, and so we end up with our numbers in sorted order. Okay. So it's a pretty simple trick, and it works well. All right. So in summary, what we've got now is LSD sort. It takes n plus r memory. It takes wn plus wr runtime. And it has this one annoying feature, which is that the runtime, if we pad out our keys with these dots, that the runtime depends on the length of the longest key. Now this approach, we will see we can actually do a little better than this, but it's actually a perfectly lovely sort. And what's cool about it is that whereas counting sort only worked for keys that were alphabetical, that is, that come from some finite range, now LSD sort will work on any sequence of alphabetical keys. Now there are still some things that might be a little awkward to try and sort this way, but this is a very general notion that will, for the most part, work out in our favor. Okay. All right. So in the next video, we're going to talk about a variant of LSD sort. And actually, in case you're feeling this, like, but what would be something that's not a string of alphabetical keys? I'm going to defer that to next lecture, not even in this sequence of lectures. And so just be aware, this is a very general notion, but there's still a little bit of wiggle room that we're going to have to play around with in the next lecture. But today, we're going to wrap up by talking not about LSD sort, but something else known as MSD sort. Okay, so I'll see you in that video.